The next application I'm going to talk about is co-electric generators, which is really important. I'm pretty sure you know why. And basically everything that we're doing now is possible because we have the power, electrical power, and they're all coming from the generator. So let's see how this generator works. So what I'm showing you here is a very simple prototype of generators. To build a generator, what you need is a magnet, you need a loop, and you need something to rotate it. It could be the windmill, it could be a water dam, like something which can help you to rotate this guy. Okay, so when you're rotating this guy, you can see the loop has an area, and this area will catch the magnetic flux. But by rotating it, the magnetic flux through this area will keep changing. And because the flux is changing, so it will constantly induce the current. Okay, so usually you can see this setup is very similar. It's very similar to a motor, except that we don't have a battery here, because this guy will generate supposedly like a generator is like a battery, which generates power, electrical power. So usually you will just have this, and this guy will eventually connect it to your house. So you can use your computer watching this video. Okay. All right, so usually, so now I wanna just take a close look at how the current is generated in this generator, like step by step. So let's say, if we have some sort of power which can rotate this loop not in this direction, in this direction with the angular velocity omega. So let's see. All right, so now say if we look from the top, so this is gonna be a bird view. Okay. If you look from the top, and then you can see the magnetic field is going to the right, because you're looking from the top, you will only see this rod, and then we are measuring the current coming from this end. Okay. They're coming from this end. If the current is coming in, it's like out of the page here. We call this positive. If the current is coming out, it will flow out in this direction from the loop, then we call this negative. So if this is into the page, it will be negative. So now let's see what's happening from 0 to 1. At 0, you can see it has a magnetic flux 3. And at 1 second, there is no magnetic flux. Okay, because at 1 second, it's rotating this way. So after 1 second, let's say it becomes horizontally in parallel with the magnetic field, okay, which catches no flux. So from 0 to 1 second, the flux through the loop is decreasing. So the loop will be unhappy and will try to compensate that. So the loop will create a magnetic field to the right, okay, to the right. If the magnetic field loop is creating a magnetic field to the right, then you will expect a current coming in this direction, okay, which means it's in this direction. If the current is in this direction, which means the current going through this wire will be out of, at this point, will be out of page. Okay. All right, so you can imagine from 0 to 1 second, the current are going to be positive. Now let's see what's happening from 1 second to 2 seconds. From 1 second to 2 seconds, you can see there is no current, there's no flux here. But now if after I rotate all the way here, then I have 3 flux. So this is no flux, this is a 3 flux. So again, your loop will be unhappy because there's a change in flux. So it will try to create a magnetic field to the left to counter it, to counter the change. To create a magnetic field to the left, then the current must go this way, right? If the current must go this way, which means it will be out of page from this end and into the page at the other end. So from 1 second to 2 seconds, you can see that current is still positive. So now let's take a look from 2 seconds to 3 seconds. From 2 seconds to 3 seconds, again, you can see the magnetic flux, it was 3 and now it's 4. So you'll get more magnetic flux. If you get more magnetic flux to the right, then your loop will try to induce a magnetic field to the left to counter the change. And to induce magnetic flux to the, to induce a B field to the left, the current, so use your right hand rule, and you can see the current will try to go this way. So while you are following my logic from here, from one to another, I will do a couple more so that you can practice. But really here, I want you to practice using your right hand rule so that you know what I'm talking about, especially about the direction. All right, so we figured that the current is going this way, which means the current will be going out of page on this end. Okay, because it's a loop. Okay. So it's still gonna be positive, but I would say it's, okay, the current here is positive. But I would say this current from 2 to 3, I would say this current is slightly smaller or less than the current from 0 to 2 seconds. Because from 0 to 2 seconds, we are talking about 3 flux change, while from 2 to 3 seconds, we're talking about 1 flux change. So I would say this one and this one has a greater current than this one, but they are all positive. Make sense? All right. So if I go from here to here, we say it's positive and it's very positive. Same here. Same here, positive, but slightly smaller. Okay, then let's see what's happening from 3 to 4 seconds. From 3 to 4 seconds, it had 4. Now it has 3. So your loop will try to create one more to keep the to counter the change. If it wants to do one more, then you can imagine the loop are going to induce the current going in this direction, okay, by right hand rule. By the second right hand rule that we're talking about. So which means here it's gonna be into the page. So this current will be negative. Okay, going from 3 to 4, it will be negative. Okay. Then from 4 to 5, you can imagine it is still decreasing, right? Like originally we had a lot, and now I decrease it down to 0. So again, I will create the current come in this direction. It's a little bit hard to see the current for this, like it's a little bit hard to see the current to do the right hand rule for this case because I supposedly field should go in this way and it's a little bit weird. So I would encourage you to look at like just a moment before the 5 second. Maybe just look at like a 0.1 second before 5 second, and then it will help you determine the direction of current. Okay, it's gonna go this way, it will be into the page again. So similarly here, so then, how do I put this? Okay, I'm gonna keep track of my current here. Current here is negative. Current from 3 to 4 is also negative. And how about from 5 to 6? So from 5 to 6, initially I had nothing. Now I have a lot more to the right. So I'll try to counter that by pointing to the left. And my field is to the left, which means my current will be going this way, which means I'm gonna go into the page here. So again, this will create a negative current if I'm measuring from this star sign, and then like so on and so forth. So you can see the bottom 4, they will all create a negative charge. Sorry, they will all create negative current. But you can imagine from 4 to 5, we are talking about a change of flux for 3. And 5 to 6 is also for 3. However, 6 to 7 or 3 to 4, it only has a flux change of 1. So I would say it's a very negative for this two, and a little bit negative for this one and this one. Now I'm gonna put all of this idea together and trying to make a plot. Okay, remember, we said from 0 to 1 second, it's very positive, a little bit positive, negative, very negative, so on and so forth. If you connect all the dots, this is what you will get. You get like a sine shape. So this is kind of a current that coming out from the power generators is an alternating current, so I'm gonna call this AC current. This is in contrast to the direct current, like one direction current that we used to talk about, like our battery. Okay, so this is the AC current. It's a little bit tricky to talk about AC current because if we want to say, oh, how much is the current? It's not like just, one line. It's not like it's 1 ampere, 2 ampere. The current is changing all the time. So to really describe the current, to describe this AC current, we want to say the strength of the current, for example. There are a few ways we can tell people. So for example, you can tell people the peak current. For example, you can say I have an AC current where the peak is at, it's like 2 ampere, it's 1 ampere, let's say. Okay. Another way to talk about this current is we can talk about its average. But the average is not just a very simple average like add them all up, because if you add up all the average, the positive and negative will cancel out. So instead of doing that, we will do another current, another average we call root mean square. Root mean square means taking all this distance, taking all the current here, square them, add them up, and then take a square root. So that's called root mean square. So this number will always be positive. It will somewhat tell you the average. Will somewhat tell you the average of this shape, of a data which has both positive and negative. So anyhow, because usually the current coming out of this power generators, it's a sine shape. So the root mean square has a very simple relationship to the peak current, which goes like this. So which goes like this. The root mean square current is pretty much the peak current divided by square root of 2. This relation is only true for a sine shape of a generator. Sorry, for the sine shape of an AC current. And what is the peak current? The peak current will depend on the number of the turns because if you have, because each loop will create a current, right? We will create a voltage, will create one EMF. If you have more loop, then you will create a lot of EMF. So it's kind of like you have a lot of little batteries. And if all these batteries, they're connected in series, then the voltage will add up, right? So you can see the number, if you have more of these loops, then you will, the total potential difference, the total EMF will be greater. So you can see this N play a role here. And this peak EMF also depend on the area and the magnetic field, which makes sense because this is essentially magnetic flux. It also depends on how fast you rotate it, because it's like this is like a 1/time. Okay, so since the EMF, this is okay. Since the EMF here is generated because of to counter the change in flux, so you can see all of them will play a role to affect my peak EMF. So for example, this N is this guy, the phi, the flux is A times B, the time is basically the rate. Okay. So exactly why this looks like this, I'm kind of briefly introduce this to you like in a dimension analysis way. There might be some factor of 2, 1, whatever. But the reason that you don't have this is because the reason that we know this equation is correct is because we actually, it's a sign shape, so we can just do the integrate. We can just calculate the flux at each moment and then do a derivative. Then you will recover this same equation. So anyhow, this is the EMF corresponding to the peak. In general, the EMF for the entire sine shape can be described by this one. Basically, I just add sine omega t to describe it. Don't worry about it. I'm not gonna ask you to do some, tedious trigonometries about this. All what you need to know is this guy, okay? Once we know that the EMF, which is the voltage, then we can take the voltage divided by R, then we can literally get the peak current, which is gonna be the value at this point. All right, so this is how you can understand the generators and actually calculate it. So that's it.